The second step in function approximation procedure is adjusting the weights Wi to best fit the training examples. Here we specify the learning algorithm for choosing the weights Wi to best fit the set of training examples. There may be many algorithms. Out of them, we need to select an algorithm which will best fit our training examples. We know that our training example is having two factors. One is B, board state, and second one is V train B, the training value for the corresponding board state. First step is to define what we mean by the best fit to the training data. This need to be specified. One common approach is we define the best hypothesis or set of weights which will minimize the squared error E between the training values and the values predicted by the hypothesis. That is given by the equation shown here. Capital E equal to summation of for all training examples which is having board state B and corresponding training values for that board state. We will take the difference between the training values and the values predicted by the hypothesis, that is VB. V train B will indicate the training value for the board state. This is being squared just to get rid of the negative values. Summation means for every training example we need to calculate this error and we need to add them together. Then we will get the capital E. That's what summation means. That will give us the total error present in all the training examples. Several algorithms are known for finding weights of a linear function that minimizes capital E. Consider an algorithm called least mean squares or LMS training rule. For each observed training example, it adjusts the weights a small amount in the direction that reduces the error. On this training example means we are increasing the weights such that the error becomes 0 or it becomes minimum. LMS weight update rule for each training example which is consisting of B, V train B, that we call it as board state, the corresponding training value for that board state. Use the current weights to calculate the V map B, means you are predicting the weights for the V map P, means you are predicting the next weight. For each weight Wi, update it as the new weight Wi is you take the older weight plus neta of V train B minus V map B into xi. Here neta is a small constant. It is in the order of 0.1, 0.2, 0.01 that moderates the size of the weight update, and xi is some feature which is associated with the training example. Working of weight update rule. When the error, that is V train B minus V map B, is 0, no weights are changed, because when you deduct V train B minus V map B, then it itself will show that there is no error at all. There is no necessity of changing the weights. Weights are appropriate, which is minimizing the error. When V train B minus V map B is positive, that indicates there is some error. Each weight is increased in proportion to the value of its corresponding feature. The weights are increased, which will reduce the error. This will raise the value of V map B, reducing the error. In the relation V train B minus V map B, suppose there is an error, and if you increase the value of V map B, then ultimately this subtraction, that is V train B minus V map, reduces. If the values of some feature xi is 0, if you see in the equation, xi is associated with the second term. So Wi becomes equal to Wi. There won't be any changes necessary at all. It indicates that there is no error at all. Its weight is not altered regardless of the training error. We are designing a learning system and our next step is the final design. The final design of Checker's learning system can be described by four distinct program modules that represent the current components in many learning systems. They are performance system, critic, generalizer, and experiment generator. Performance system. It is the module that must solve the given performance task by using the learned target functions. Tasks may be many. It takes an instance of new problem, that is, it takes the new game as input and produces a traces of its solution. It generates game history as output. Next step is the critic. In critic, the input is history or trace of the game and it produces output the set of training examples of the target function. The generalizer step takes input training example and it produces the output hypothesis, the estimate of the target function. Generalizer generalizes from the specific training examples, hypothesizing a general function that covers these examples and other cases beyond the training examples. The experiment generator, it takes the current hypothesis as input and outputs a new problem, that is initial board state it will produce for the performance system to explore. Its role is to pick the new practice problems that will maximize the learning rate of overall system. Finally, the sequence of design choices made for the Checkers program is summarized in the figure shown. First step will be determine type of training experience. What are the options we have got? It may be game against experts, or it may be game against self, or table of correct moves. We have selected to play against itself, means the program is playing against itself. Next step is determine the target function. Again we have got the options. It may be board move or it may be board values. If you remember the equation, we have taken the board values. Next step is determine representation of learned function. It may be polynomial, it may be linear function of 6 features, it may be artificial neural network. If you remember, we have taken 6 features, that is x1, x2, x3, x4, x5 and x6. Those may be number of black pieces on the board, number of red pieces on the board and so on. We have selected linear functions of 6 features. Next step is determining the learning algorithm. Here also there are many options. We have selected the algorithm gradient descent that will complete the design step.